The thunder of the Panzerfaust warhead hitting the Sherman's right side sounded like someone had dropped a cathedral bell into a steel foundry. Staff Sergeant Michael Donovan felt the entire 30-ton tank shudder beneath him as smoke filled the interior, and his eardrums screamed in protest. Through the haze, he looked down into the crew compartment, fully expecting to see the molten copper jet that should have punched through their armor and killed everyone inside. But his loader was staring back at him, eyes wide with shock but very much alive. The driver cursed in disbelief. The bow gunner had his hands pressed against the hull, feeling for the penetration hole that regulations insisted should be there. It was not there. The improvised armor, 3 inches of welded track links backed by a half-inch steel plate, and sandbags that other crews had mocked as Donovan's junkyard special, had absorbed the shape charge before it could reach the factory hull. In the narrow streets of Aachen, Germany, in October 1944, a tank commander who had broken every engineering regulation in the Army Technical Manual had just saved 5 American lives, and he was not done yet. If you are watching this story unfold, take a moment to subscribe to this channel and let us know in the comments where you are watching from today. This is the untold story of how ordinary tank crews, armed with welding torches and scrap metal, forced the United States Army to admit that soldier ingenuity sometimes knew better than engineering doctrine. 3 months before that morning in Aachen, in the hedgerow country of Normandy, Corporal James Whitaker watched through his periscope as a Sherman from Baker Company burst into flames 50 yards ahead of him. The tank had been advancing through a narrow lane between centuries-old earthen walls when the German hollow charge warhead struck its right side at a perfect 90-degree angle. The explosion was not particularly dramatic from outside, just a sharp crack and a flash of white light. But 3 seconds later, flames erupted from every hatch as stored 75mm ammunition cooked off in a chain reaction. Whitaker counted 4 men bailing out. There should have been 5. The loader never made it. The heat radiating from that burning Sherman was so intense that Whitaker could feel it through his own armor 200 feet away. The smell of burning rubber and something worse, something no soldier ever wants to describe, drifted through the summer air. In the hedgerow country they called the bocage, American tankers were learning a lesson that no training manual had prepared them for. The Sherman they had been promised would protect them was burning like kindling against weapons it was never designed to face. The M4 Sherman had rolled off assembly lines in Detroit with 51 millimeters of side armor, adequate protection against the French and Polish tanks American planners imagined facing in 1940. But the war had evolved faster than the specifications. The German Panzerfaust worked on a principle that rendered raw armor thickness almost irrelevant. When its hollow charge detonated, it focused explosive force into a superplastic jet of molten copper traveling at 6 kilometers per second. That white-hot stream could penetrate up to 200 millimeters of steel, burning through the Sherman's side armor like a blowtorch through wet cardboard. The turret sides were even thinner, just 38 millimeters. In the close quarters fighting of Normandy's hedgerows, where narrow lanes bordered by earthen walls thick enough to stop tank fire created perfect ambush conditions, German infantry could approach within 20 meters before firing. At that range, the Panzerfaust rarely missed, and when it hit, the mathematics of survival became brutally simple. If your Sherman took a shaped charge hit and did not immediately explode, you had approximately 5 seconds to get out before the ammunition ignition turned your crew compartment into a blast furnace. By late June 1944, Baker Company had lost 11 Shermans to hollow charge weapons in hedgerow fighting. 8 of those tanks had burned completely, killing or badly burning 23 crewmen. German troops had given the Sherman nicknames that captured its terrible vulnerability. Tommy Cooker in Europe, Ronson in reference to the cigarette lighter brand, because it lit first time every time. Every tanker in the battalion understood the arithmetic. The Sherman was fast, reliable, and mechanically superior to most German tanks. Its radial engine started in any weather. Its transmission rarely failed. Spare parts flowed from American factories in quantities the Germans could only dream of. But in close combat against infantry armed with Panzerfaust or Panzerschreck rocket launchers, all that mechanical excellence meant nothing if the armor could not stop the weapons being fired at it. Standard doctrine offered no solutions. The tank had been designed for mobile warfare across open terrain, not the medieval siege combat of hedgerow country, where every advance was measured in fields cleared rather than kilometers gained. And summer in Normandy meant hundreds more fields, thousands more hedgerows, and an unknown number of German infantry teams waiting with weapons specifically designed to kill the tank the United States Army had bet its entire armored doctrine upon. Something had to change, and it would not come from Detroit or the Ordnance Department. It would come from the crews who refused to die in vehicles their own command insisted were adequately protected. The first unauthorized modification appeared on July 2, 1944, in a maintenance area behind the lines near St. Lo. Sergeant Thomas McKenna stood beside his Sherman, studying a pile of spare track links stacked next to the maintenance tent. Each T-48 steel track link weighed 56 pounds and measured roughly 5 inches wide. McKenna had been watching the Panzerfaust hits for weeks, studying the penetrations, talking to survivors, examining the burned-out hulks that dotted the Norman countryside. He had noticed something that the engineers back in Aberdeen, Maryland, had apparently missed. The hollow charge jet needed time and space to form properly. If something disrupted that jet before it reached the main armor, even briefly, the penetration depth dropped dramatically. Layered obstacles spaced at intervals could theoretically bleed a shaped charge's energy dry before it ever touched the hull. McKenna's plan was simple. Weld track links in overlapping layers onto the tank's vulnerable side sponsons and turret, creating additional standoff distance that might disrupt the copper jet before it reached the factory armor. What Sergeant McKenna was about to do violated explicit Army Ordnance Department regulations. Track links were not armor-grade steel. They were medium carbon steel designed for flexibility and wear resistance, not ballistic protection. Welding anything to factory armor plate risked creating stress points that could cause cracks under shell impact. And each track link added weight to a tank already operating near its 33-ton design limit, stressing the vertical volute spring suspension and final drives beyond their engineering specifications. The technical manual was absolutely clear. Unauthorized modifications to armored vehicles were prohibited and subject to disciplinary action up to and including court-martial. McKenna welded the track links anyway. He worked through the night using an arc welder borrowed from the maintenance platoon, creating a fish-scale pattern of overlapping steel across the right sponson, where the last Panzerfaust had nearly penetrated. His crew helped, positioning links while he tacked them in place, then running continuous welds along the edges. The sparks flew in the darkness like orange fireflies, the arc's electric hum cutting through the distant rumble of artillery. By morning, his Sherman looked nothing like the clean vehicles that had rolled off the Detroit assembly lines. It looked like something from a medieval armorer's fever dream, bristling with welded metal that officially did not exist and was not supposed to work. Other crews watched with a mixture of skepticism and interest. Some mocked the modification as McKenna's junkyard special. Others quietly took notes on his welding pattern, mentally cataloging where he placed each link and at what angle. 4 days later, on July 6th, McKenna's improvisation faced its first combat test outside the village of Carentan. A Panzerfaust team hidden in a farmhouse cellar fired at a Sherman from 15 meters, the hollow charge warhead struck the right sponson exactly where McKenna had welded 3 layers of track links. The explosion was spectacular, louder than a standard hit, with more smoke and fragmentation as the track links absorbed and dispersed the shaped charged jet's energy. McKenna felt the impact through his boots, heard the metallic shriek of stressed steel, smelled the acrid smoke of burned explosive compound. But when he checked for penetration, he found something remarkable. The outermost track link had been blown completely off, the steel twisted and partially vaporized. The middle link was cracked and partially melted, showing the path where the copper jet had tried to bore through. But the innermost link and the factory hull armor behind it were intact, not a scratch on the paint. His crew was shaken but uninjured. The improvised standoff armor had worked, not perfectly, but well enough to turn a certain penetration into a survivable hit. Word spread through the battalion faster than official orders ever could. By mid-July, crews across the 2nd Armored Division were welding track links, bolting salvaged German armor plate, and piling sandbags onto their Shermans. Some modifications were sophisticated, with carefully spaced steel plates creating precise air gaps designed to disrupt shape charges at optimal distances. Others were crude, just sandbags stacked 3 deep on glacis plates and held in place with chicken wire and prayers. A few crews even poured concrete over vulnerable areas, though the added weight and spalling risks made that approach controversial, even among the improvisers. The tanks that resulted looked nothing like military equipment. They looked like armored beasts assembled from battlefield debris by desperate men who had decided that survival mattered more than regulations. But on July 18th, a captain from the Ordnance Department arrived at McKenna's unit with orders to inspect unauthorized tank modifications. The captain carried a copy of the technical manual, photographs of modified Shermans taken by supply officers, and explicit instructions from command. Remove all improvised armor immediately. Return tanks to factory specifications. Identify the soldiers responsible for violating regulations. The message from the Army's engineering establishment was unmistakably clear. Survival instincts did not override engineering doctrine. Crews who continued modifying their tanks would face consequences that no amount of welded track links could protect them from. The captain spent 3 hours documenting violations, writing down names, and lecturing crews about suspension stress tolerances and metallurgical principles. The tankers listened politely, nodded at appropriate moments, and waited for him to leave. Then they went back to welding. 6,000 miles across the Pacific on an island that would become synonymous with American sacrifice, a different kind of improvised armor was saving lives against a different kind of threat. On February 21, 1945, Gunnery Sergeant Robert Haze, crouched behind his Sherman on the black volcanic sand of Iwo Jima, watching Japanese infantry emerge from a cave entrance 30 meters away. Haze had been a tank commander for 18 months fighting through Tarawa and Saipan, and he understood exactly what was about to happen. The Japanese did not have Panzerfausts or Panzerschrecks. Their anti-tank capabilities were limited to 47mm Type 1 guns, magnetic mines, and satchel charges. But what they lacked in ranged firepower, they compensated for with suicidal determination and tactics specifically designed to exploit the Sherman's greatest vulnerability, its crew. The Japanese infantry assault technique was methodical and terrifying. A 3 to 9 man squad would target an isolated tank. One soldier threw smoke grenades to blind the crew and force them to button up inside, unable to see approaching threats. Another threw fragmentation grenades against the hull to keep hatches closed. A third placed mines on the tracks to immobilize the vehicle. Then the final assault team would swarm the tank, prying open hatches with crowbars, dropping grenades into crew compartments, or placing satchel charges directly on the engine deck. The Sherman's armor, more than adequate against Japanese tank guns, offered absolutely no protection against infantry physically climbing aboard and forcing their way inside to kill the crew by hand. Haze had lost 2 tanks to these tactics at Saipan. The first had been immobilized by a magnetic mine, then swarmed by infantry, who forced open the loader's hatch and dropped grenades inside, killing 3 of his friends. He could still hear their screams when he closed his eyes. The second tank had its engine destroyed by a satchel charge placed on the rear deck. After Saipan, Haze began improvising countermeasures that had nothing to do with stopping projectiles and everything to do with preventing infantry from physically accessing his tank. He welded 2-inch wooden planks to the sponsons, creating a barrier that made climbing difficult. He added wire mesh cages over the hatches, requiring tools to access the openings. Most controversially, he welded upturned nails, hundreds of them, to every horizontal surface: hatches, engine decks, fenders. The modifications looked crude, almost medieval, like something from a torture chamber rather than a modern battlefield. But they worked. On Iwo Jima, when the Japanese squad attempted to swarm Haze's tank, they discovered that climbing a Sherman covered in wooden planks, wire mesh, and upturned nails was nearly impossible under fire. The wooden planks provided no handholds for grasping fingers. The wire mesh prevented grenades from being dropped through hatch cracks. The nails made it impossible to place satchel charges without severe hand injuries. Haze's bow gunner opened up with his .30 caliber machine gun, while the assistant driver used a submachine gun through a firing port. The Japanese assault failed, leaving 5 enemy soldiers dead around the tank and Haze's crew uninjured inside their improvised fortress. The black sand of Iwo Jima soaked up the blood as the surviving attackers retreated into their caves. This is exactly the kind of story that deserves to be shared. If you are finding value in this deep dive into history, consider hitting that like button and sharing this video with someone who appreciates the courage of ordinary soldiers doing extraordinary things. Your support helps bring more of these forgotten stories to light. Other Marine tank crews across the Pacific had made similar discoveries independently. At Tarawa, crews had added concrete to glacis plates for protection against 37mm guns. At Saipan, wooden planks became standard crew modifications after multiple tanks were lost to infantry assault. On Iwo Jima, the improvisations reached their peak. Wood, concrete, steel plates, wire mesh, spare track links, and upturned nails all combined into uniquely customized tanks that looked nothing like factory specifications. Each Sherman became a reflection of its crew's particular fears and experiences, modified against the specific threats they had survived. The modifications spread through the same informal networks that had carried track-link welding across Europe. Tank commander to tank commander, maintenance crew to maintenance crew, knowledge passed through demonstration rather than official training. But like their Army counterparts in Europe, Marine tank crews faced official resistance from technical representatives who issued warnings that unauthorized modifications voided warranties, stressed suspensions, and violated maintenance protocols. Back in the United States, at the Army Ordnance School in Aberdeen, Maryland, Colonel William Barclay sat in his office in August 1944, reviewing field reports and photographs that filled him with professional alarm. Barclay had spent 23 years studying armored vehicle engineering. He had overseen Sherman production specifications and understood better than most why the regulations existed. The photographs showed Shermans loaded with sandbags, concrete, welded track links, and salvaged armor plate, modifications that violated every engineering principle he had spent decades establishing. And according to the reports, crews were continuing these practices despite explicit prohibition orders. The Sherman suspension system had been engineered with precision tolerances. The vertical volute spring suspension used 30-inch diameter bogie wheels and vertical coil springs designed to support a combat weight of 30 to 33 tons. Each track link added weight. A 3-layer application across both sponsons meant adding nearly 2,000 pounds. Sandbags were worse. Wet sand could add 4 to 5 tons. Concrete was catastrophic, potentially adding up to 8 tons when applied heavily. At 38 to 40 tons, the Sherman's final drives, transmission, and bogies operated beyond their design specifications. Field maintenance reports documented increased failure rates, broken bogie springs, stripped final drive gears, transmission overheating. Tanks that survived enemy fire were breaking down mechanically from modifications meant to protect them. The metallurgy concerns were equally serious. Track links were not armor-grade steel. They were medium carbon steel designed for flexibility and wear resistance, not ballistic protection. When struck by anti-tank rounds, the track links could actually normalize incoming projectiles, changing their trajectory to strike factory armor at more favorable angles. German technical intelligence reports from late 1944, captured after the Battle of the Bulge, included analysis of destroyed American tanks. German engineers had documented cases where improvised armor appeared to have worsened penetration outcomes by channeling rounds toward weaker armor zones or creating small inside crew compartments when the improvised armor failed catastrophically. Concrete presented its own hazards. Under impact, concrete did not stop projectiles. It shattered into fragments that could be as deadly as the incoming round itself. Medical reports from field hospitals described crew casualties from concrete spalling, fragments that penetrated soft tissue, blinded soldiers, or caused traumatic injuries inside crew compartments even when the main armor remained intact. The concrete's weight also concentrated stress on welds and mounting points, creating fatigue cracks in factory armor that could propagate under the shock of combat movement or shell impact. Yet the data from properly maintained factory specification Shermans validated the original engineering. In ideal tactical conditions, fighting at ranges beyond 500 meters, using terrain for cover, employing combined arms tactics with infantry support, the Sherman performed exactly as designed. Its reliability was exceptional. Mechanical breakdown rates were lower than any contemporary tank, and crew survivability in vehicles used according to doctrine was acceptable, at least on paper. The tension Colonel Barclay faced was that combat had created conditions the original specifications never anticipated. The Sherman had been designed for mobile warfare, breakthrough operations, exploitation, pursuit. The designers assumed tanks would fight at medium to long range, supported by infantry and artillery, with time for maintenance between engagements. None of those assumptions held in Norman hedgerows or on Pacific beaches, where close quarters fighting, limited maintenance time, and immediate survival needs made engineering considerations seem dangerously irrelevant to the men inside those steel boxes. Barclay's reports to the Ordnance Department acknowledged what could no longer be denied. Crews were modifying tanks because standard specifications were not keeping them alive, and some of those modifications, despite their engineering flaws, were producing better survival rates than factory doctrine predicted. By September 1944, Barclay began drafting recommendations that would fundamentally change how the Army approached field modifications. The unauthorized techniques should be studied systematically, tested under controlled conditions, and, if effective, incorporated into official practice with proper engineering support. But the memorandum would also carry warnings. Most field modifications were counterproductive, some were actively dangerous, and all carried risks that only proper engineering could mitigate. The path forward required balance, respecting soldier ingenuity while applying engineering discipline to separate innovations that worked from experiments that killed. On October 22, 1944, Lieutenant Colonel James Morrison stood at the Aberdeen Proving Ground in Maryland, watching engineers conduct live fire tests on a Sherman that looked like it had been assembled from a scrapyard. The tank was covered in welded track links arranged in a specific fish scale pattern, spaced steel plates mounted 6 inches from the hull, and carefully positioned sandbag arrays. But this was not a field improvisation. It was an official Ordnance Department test vehicle, constructed to replicate the most successful modifications that crews had been making for months across two theaters of war. Morrison had been tasked with answering the question that command could no longer avoid. Did improvised armor actually work, or were crews wasting weight and mechanical reliability on modifications that provided only psychological comfort? The evidence had been building since August. Statistical analysis units at the Ordnance Department had compiled data from hundreds of tank loss reports, comparing penetration rates between modified and unmodified Shermans. The numbers told a story that engineering prejudice could not dismiss. Shermans with properly applied track-link armor, 3 layers welded at 30-degree angles to create standoff distance, survived Panzerfaust hits at rates 20 to 30% higher than factory specification vehicles. Spaced armor using salvaged steel plate mounted 4 to 6 inches from the hull disrupted shaped charged jets before they reached factory armor. Even sandbags, when properly placed and kept dry, provided measurable protection against small-caliber anti-tank weapons and infantry rockets. The Aberdeen tests confirmed what tankers had discovered through necessity. Engineers fired, captured Panzerfausts and German 75mm rounds at the test vehicle from ranges matching combat conditions. Track links arranged in overlapping layers created multiple disruption points for shaped charged jets, dispersing the molten copper stream before it could achieve full penetration. Spaced armor worked even better. The hollow charged jet expended most of its energy penetrating the outer plate, leaving insufficient force to breach the main hull. The modifications were not perfect. Penetration still occurred in roughly 40% of hits, but that was far better than the near-certain penetration of unmodified side armor, and in tank warfare, a 40% chance of survival was infinitely better than zero. By November 1944, the Ordnance Department began what it euphemistically called Theater Armor Enhancement Guidance, official authorization for specific field modifications that testing had validated. Technical Bulletin TB Ord 353 quietly authorized track-link application using prescribed welding patterns and weight limits. Salvaged armor plate could be mounted as spaced armor provided it did not exceed 2,000 pounds total added weight. Sandbags were authorized for glacis protection only, with strict instructions to remove them if they became waterlogged. What had been court-martial offenses in July were official field expedients by December. The crews who had been threatened with discipline for trying to survive were now being trained in the very techniques they had pioneered months earlier. More importantly, production priorities shifted. The M4A3E2 Jumbo Sherman, which had been in development since early 1944, entered accelerated production. The Jumbo featured factory-applied additional armor, 100 mm frontal armor versus the standard 51 mm, and reinforced suspension components to handle the 38-ton combat weight. Only 254 Jumbos were produced, but they validated the principle that heavy armor could work when properly engineered from the start. Official armor kits began reaching frontline units in January 1945. Prefabricated track-link assemblies with mounting brackets, spaced armor plates with proper standoff dimensions, and reinforced suspension components to handle the additional weight. The Army had finally caught up with what its tankers had been proving for 6 months, but the vindication carried bitter weight. Between June 1944 and January 1945, the 7 months it took the Army to study, validate, and authorize improvised armor techniques, thousands of Sherman crewmen had died in factory specification tanks. How many would have survived if the track-link configurations discovered in July had been immediately tested, standardized, and distributed as official kits? How many crews had burned in tanks that lacked armor modifications other units had perfected months earlier? The military had adapted, had learned from field innovation, had incorporated soldier ingenuity into doctrine, but it had done so at the pace of bureaucracy, while men died at the pace of shaped charge penetration. And the cost of that delay was measured in casualty figures that would haunt armored warfare doctrine long after the last Sherman rolled off the assembly line. Not every improvised armor modification saved lives. On September 8, 1944, a Sherman from Charlie Company, 3rd Armored Division, broke down during an advance outside Mons, Belgium. The tank, nicknamed Iron Duke, had been heavily modified by its crew over the previous 6 weeks. Track links covered every accessible surface. Sandbags were piled 4 layers deep on the glacis. Concrete had been poured over the sponsons. Steel plates salvaged from 3 destroyed German vehicles were bolted to the turret. The modifications had taken weeks to apply and added an estimated 7 tons to the vehicle's combat weight. When Iron Duke's transmission seized during an advance under fire, the tank became a 39-ton immobile target that had to be abandoned. German artillery destroyed it 3 hours later. The crew survived by evacuating on foot, but their tank and all the protection they had labored to create was lost not to enemy action, but to mechanical failure caused by modifications meant to save them. The failure points in improvised armor were numerous and often unpredictable. Excessive weight stressed the Sherman's vertical volute spring suspension beyond its design tolerances, causing bogie spring failures, final drive gear stripping, and transmission overheating. Maintenance records from late 1944 documented that heavily modified Shermans experienced mechanical breakdown rates 30 to 40% higher than factory specification vehicles. Some crews found themselves stranded in combat zones, not because of enemy fire, but because their suspension had collapsed under the weight of armor that was never engineered into the vehicle's load calculations. Concrete modifications proved particularly problematic. On October 3, 1944, a Sherman from the 4th Armored Division took a 75mm anti-tank round to its concrete-covered right sponson near Aracourt. The concrete did not stop the round. It shattered on impact, creating a spray of fragments that killed the loader and seriously wounded the driver. Post-battle analysis showed the concrete spalling had caused more casualties than the actual penetration would have on bare armor. Medical reports from evacuation hospitals documented similar injuries across multiple units. Crews blinded by concrete fragments, soldiers with traumatic wounds from spalled material, cases where improvised armor had turned non-penetrating hits into casualty events. Some track-link configurations actually worsened armor effectiveness. German technical intelligence reports captured after the Battle of the Bulge included analysis of destroyed American tanks that revealed an unexpected phenomenon. Improperly spaced track links could normalize incoming anti-tank rounds, changing their trajectory to strike factory armor at more favorable penetration angles. Instead of deflecting projectiles, poorly configured improvised armor sometimes guided them toward weaker zones. The crews who applied these modifications had no way to know if they were making their tanks more vulnerable. They were operating on instinct and observation, not engineering analysis. A few crews faced legal consequences for modifications that caused mechanical failures or violated regulations before official authorization arrived. On August 12, 1944, a sergeant from the 2nd Armored Division was brought up on charges after his heavily modified Sherman broke down during combat, blocking a narrow road and delaying an entire company's advance for 2 hours. The charges were eventually dropped when his battalion commander intervened, arguing that the sergeant had been trying to protect his crew using the only methods available. But other cases proceeded to courts-martial, with soldiers receiving reprimands or demotions for violations of ordnance regulations that would be authorized as official field expedients just months later. Yet, despite the failures, the overall survival data told an undeniable story. Units that systematically employed effective armor modifications, properly spaced track links, limited weight additions, and avoidance of concrete experienced tank loss rates 15 to 25% lower than units that maintained factory specifications. The innovations worked not because they were perfect, but because even imperfect protection was better than none in the brutal mathematics of armored warfare. The crews who died from counterproductive modifications were casualties of a learning curve that should have been climbed in peacetime testing grounds, rather than on battlefields where mistakes were measured in burning tanks and dead soldiers. By war's end, the lessons purchased through trial and error had been systematically documented. The Aberdeen Proving Grounds post-war analysis of improvised armor included detailed failure mode studies, which modifications worked, which failed, and why. Every prohibition in the official armor enhancement guidelines existed because some crew had tried it, failed, and either survived to report the lesson or died teaching it to others. The knowledge that went into Technical Bulletin TB-ORD 353 and the M4A3E2 Jumbo Sherman's design came not from engineering theory alone, but from tankers who had gambled their lives testing modifications that no manual addressed. Some of those gambles saved crews, others killed them. All of them contributed to an evolution in armored warfare doctrine that transformed how military engineering approached field modifications, not as violations to be punished, but as innovations to be studied, validated, and incorporated when they worked, or understood and prohibited when they did not. The story of improvised Sherman armor revealed something deeper than engineering adaptation. It exposed a fundamental difference in military culture that helped define American effectiveness in mechanized warfare. In the years after the war, historians studying tank loss rates across all combatant nations discovered a pattern that industrial production alone could not explain. American armor units achieved survival and mission success rates that exceeded German predictions by significant margins. Despite facing technically superior tanks like the Panther and Tiger, American tankers survived encounters at rates the Wehrmacht's tactical models said were impossible. The difference was not in specifications or firepower. It was in what the system allowed crews to do when doctrine failed. German armored forces also attempted improvised armor modifications. Panzer crews welded spare track links to hull sides, applied Zimmerit anti-magnetic paste, and mounted spaced armor plates. But German military culture emphasized centralized command and strict adherence to engineering specifications. When modifications were attempted, they required approval through formal channels that moved at the pace of bureaucracy. Field commanders who authorized unauthorized modifications faced disciplinary action. The German military even issued an official newsletter in 1944, the Nachrichtenblatt der Panzertruppen, warning against most improvised armor techniques. The system valued engineering purity over tactical adaptation, and the casualty data reflected that choice. German tank crews facing the same threats as American tankers lacked the cultural permission to improvise solutions, even when those solutions might save their lives. American military culture, by contrast, had always emphasized decentralized decision-making and individual initiative within mission parameters. The same principle that empowered infantry sergeants to adapt tactics on the ground extended to tank crews facing impossible situations. When Sergeant Thomas McKenna welded track links to his Sherman in July 1944, he was not just breaking regulations, he was embodying a military culture that trusted sergeants to solve immediate tactical problems using whatever resources and ingenuity they possessed. That trust carried risks. Some modifications failed catastrophically. Some crews died from improvised armor that proved counterproductive. But the system's willingness to tolerate experimentation, study outcomes, and incorporate successful innovations created tactical flexibility that rigid command structures could not match. The post-war analysis compiled by the Army Armor School documented the results with statistical precision. American Sherman loss rates from shape-charge weapons declined from approximately 65% penetration-to-kill ratio in June 1944 to 42% by March 1945. Part of that improvement came from better equipment: the M4A3E2 Jumbo, improved armor kits, the 76mm gun. But statistical analysis revealed that units using authorized field modifications showed survival rate improvements months before new equipment arrived. The innovation came first from crews adapting to battlefield reality, then from institutional resources following where soldiers had already led. That sequence, field innovation preceding official doctrine, became the defining characteristic of American armored warfare's evolution through the war. Sergeant Michael Donovan survived the war and returned to Detroit, where he worked in the same factory that had built his Sherman. His tank, Lucky Strike, was scrapped in 1946. Its improvised armor was melted down with thousands of other war surplus vehicles. Donovan's service records mentioned his Bronze Star for valor, but said nothing about the armor modifications that had saved his crew at Aachen, or the techniques he had pioneered that eventually influenced official doctrine. The same was true for Sergeant McKenna, Gunnery Sergeant Haze, and thousands of other tank commanders whose names appeared in unit rosters but never in engineering histories. They were ordinary soldiers given basic mechanical training, inadequate armor protection, and impossible tactical situations. They responded by thinking rather than simply obeying, by adapting rather than waiting for permission, by prioritizing survival over regulations written for circumstances that combat had made obsolete. The lesson extended beyond armor. American success in mechanized warfare came not just from producing 50,000 tanks, but from empowering the crews inside those tanks to identify problems and innovate solutions. That same flexibility appeared in every domain where American forces faced unexpected challenges. Aircrews modified aircraft beyond technical manual specifications to improve combat performance. Infantry developed tactics that were not in field manuals. Artillery forward observers created fire control procedures that exceeded official doctrine. In every case, the pattern was identical. Combat necessity drove field innovation. The institution initially resisted, and eventually doctrine adapted to match what soldiers had proven worked. The improvised armor was not just welded metal. It was proof that in war, the courage to question doctrine can be as essential as the courage to follow it. The tank crews who violated engineering regulations to protect themselves carried a burden that peacetime soldiers never face. They gambled mechanical reliability against immediate survival, knowing that failures would be punished while successes might go unrecognized. Some of those gambles failed, killing crews or destroying tanks. But more gambles succeeded, saving soldiers who would have died if their commanders had rigidly enforced specifications designed for tactical conditions that no longer existed. And when the institution finally studied what those crews had been doing, validated the effective techniques, and incorporated them into doctrine, armored warfare took a step forward that influenced tank design and field modification policy through Korea, Vietnam, and into the modern era. The principle of allowing controlled field modifications, testing their effectiveness, and incorporating successful innovations into official practice became standard military engineering doctrine. Today's military vehicles carry lessons learned from those desperate welds in Norman hedgerows and on Pacific beaches. Explosive reactive armor, cage armor, and modular protection systems all trace their conceptual ancestry to sergeants with welding torches who decided that keeping their crews alive mattered more than following rules written by engineers who had never faced a Panzerfaust at 15 meters. If this story has moved you, if you believe these forgotten heroes deserve to be remembered, then do something about it. Subscribe to this channel. Share this video with someone who appreciates what ordinary people can accomplish when their lives depend on ingenuity and courage. And leave a comment telling us which moment struck you most powerfully. The track links welded to Sherman's in Normandy in 1944 were more than improvised protection. They were the beginning of a doctrinal evolution that recognized soldier ingenuity not as a violation to be punished, but as an innovation to be studied, validated, and honored when it saved the lives of those brave enough to try.